Okay, picking back up with our example 1 from section 4.5, graphing curves with calculus. What's so important is right now, I think I want to just stress that students in accelerated math analysis, really a pre-calculus class, will have graphed these functions completely without calc at all. And if we look back at our function, you could see that both the x minus 4 and the x plus 3 are raised to the 1. When denominators are raised to odd powers, remember what we said in class, that means when you're dealing with an odd power, you've got a kung fu fighter kind of a pattern, meaning at the vertical asymptote, you're going to see opposite directions, one up, one down. You can see that that's exactly what's happening here and here. The x minus 4 is raised to the 1. The x plus 3 is raised to the 1. That's indicative of going in opposite directions around your vertical asymptote. If you believe that this curve is going down here, you'd believe it's going upwards over here. Likewise, it would be coming up over here. Having these opposite directions, you can see that you'd get a shape that would look something like so. By the way, by way of comparison, if one of these denominators would have been raised to the second power, well, remember then you would have seen something more like the volcano graph, where by the vertical asymptote, you have the same direction. You have your curves going up and up or down and down. Now, so very often kids will look at this and they'll say, well, so I don't need calculus really to work this out. Well, that still begs the question, what about that 22.954? At 1.045, you can certainly believe that we're going to be getting some sort of a relative maximum. We might even confirm if that's really happening. Look, you could go to a number line coming back here. And I do want to just tell you that because we're going to be testing the first derivative, this can be a lot more difficult to check. I wanted to show you something really nice with the graphing calculator. You could choose values of x to plug in. I'm going to choose just to the left of -3. I'm going to test -4 and plug that in for x. And tell you what, right now when I hit store from now on, whenever I type x, it's going to think of that as the number -4. If I go second enter, you can see I've already entered in my first derivative, typing it out exactly. You'd get something positive. You'd get a positive 51/8. That means f would be increasing there. What's between -3 and 1.045? Well, a 0. We don't even need a 0 to be plugged in. We could just plug it in right in here and see what's happening. Your numerator is positive. Your denominator is positive. You would guess that, hey, we get something positive, and indeed you do. And then you'd think, well, wow, what's that going to look like on the graph? Well, we'll talk about that. Let's go to the right of 1.045. Maybe we could test x equals 2. You can think, well, what's going to happen there? Well, let's get the calculator up and go 2, store that in for x. Then what? You could retype that out as the second derivative, but hey, I already did that once as a time saver. You can see you get something negative. That indicates that your curve is going to be decreasing. Your curve is going down. F is decreasing when your first derivative is negative. How about to the right here, between 4 and 22.954? Well, my goodness, you could say, how about I test, something like 21? You're free to test whatever you'd like, but we're going to hit second enter again, and look at that. With scientific notation, times 10 to the -4th, bottom line is we see something negative. So that means our curve is decreasing. Finally, let's plug in something to the right of 22.94. Let's maybe store 23 in there and see what happens. Now, it only would take a second to get that confirmation. but what we're seeing is we get something positive. So look what's happening. If you're looking here, you'd get a relative maximum at 1.045. That's certainly what we would be guessing right here. You could see between -3 and 4, your curve goes up, it goes down. But look at 22.954. Hidden behavior. This is totally hidden behavior. Evidently, we're going to have a relative minimum. So how do we clean that up? Well, we're going to have to show that our curve's going to be coming down. It's evidently going to cross this asymptote somewhere. It's going to have a minimum, and then it's going to come back up and get close to our asymptote once again. That's where calculus can really become helpful. No one, I think, even working this out, would have thought, oh, there's another relative extrema in this problem. If you just looked at the graph of the original problem, you would think that this curve, in fact, is going to never even touch that y equals 3 horizontal asymptote. You could get confirmation that it does, though. It's definitely something that you can validate. You can plug in that 22.954 into the original function to find what that minimum value is. It's going to be awfully close to 3. By the way, what we did do in class, you can see we actually typed that function out. And then as we were graphing this out, I extended the x max. You can see I had the x max actually go up to 30. And sure enough, when you hit trace, you can see what's happening around that 22. You can see, hey, we're below this y equals 3. How about that? But you can see at 22.3, we're at 2.933. At 22.7, we're at 2.933203. And then all of a sudden we start, going back up. You can see what's happening. You're definitely achieving that minimum. So that's hidden. It's visually on the calculator. You wouldn't even think of that as being a minimum point. The calculus shows you that it indeed is. So that's it for this example.